Okay, welcome to class. So, a couple things today. First off, we'll start with the mystery prize winners for the best presentations. And these were Christian's determinations, so I had no part in this. First prize was the heat treatment on steel by Elise, Joseph, Nicole, Emma, Takara, and Robert. Second prize was alloy heat treatment by Riley, Alex, Matt, and Philip. And third was the perfect snow by Matt, Warren, Liam, Ari, Zach, and Zach. So, to commence with the mystery prizes, the number one group, you guys win a box of mysterious treats from Jordan. I think they're baklava, because I had one like it before and it was pretty awesome. The second prize, so you guys can claim that. The second prize and third prize get to pick between stuff that was left in the class and stuff that I was given that I no longer want. So, second group, 1, 2, 3, 4 of you guys can come up. You have such things to choose as the mysterious wood carving from China. You have the mysterious giant banner from China, or a bunch of water bottles. So come and take your picks. And whatever you don't take, the other groups get a bunch of water bottles. So help yourselves.
I'll take
it could be amazing. That could also be amazing.
Thank you.
One each. And for your group mates, wherever they're at, give them these.
All right. Thank you.
And then the final people, come grab a water bottle at the end of class. Or now. That one was also left. I'm guessing it's fair game.
Oh, you can't go. I want the big one. No, I want the big one. What?
Okay, we'll start with our reading quiz for the day. And the very first question is the following. It says, a MOSFET is A, an updated mullet, B, a device where the gate is shorted to the drain, C, a transistor with two p-type islands in an n-type substrate, or D, a type of p-n rectifying junction. Okay, answers in. We're going to move to the next question. Answers in. Getting closer. Okay, we're going to end this one. You can just let me know. Okay. That's fantastic. I expected worse on that one. That's great. That's wonderful. Okay. Forgive that I'll have to make this a little bit bigger. But the question says, okay, for the following figure of carrier concentration versus temperature, which corresponds to the intrinsic region? Is it group 1, 2, or 3? And that's A, B, or C. Yeah, 1, 2, or 3 is A, B, and C. So which one is the intrinsic region? Is that 1, 2, or 3? Plotting carrier concentration versus temperature. Okay, answers in. 1, 2, or 3. Next question. Okay. It is 3. Yeah, so that's 70% of people. Okay, how about this question? Conducting polymers, something that seems counterintuitive. Most polymers we think are not conducting. But those that are conducting typically have A, alternating double and single bonds or aromatic groups, B, silicon atoms along the polymer backbone, C, large side groups, or D, a 3D network structure. Okay, get your answers in. A, B, C, or D. Okay, we're gonna wrap this one up. Yeah, A was the correct one. Okay. All right, let's talk about the rest of the chapter then. So today we're going to do the following. We introduce the idea that band gaps form, that electrons can't just occupy any energy level increasing up, right? There's only certain bands where they can occupy, right? So we're then going to talk about the Fermi level, what that is, and we'll just define something called the Fermi-Dirac distribution, which basically tells you where are these electrons at any given temperature. We'll describe electron mobility and how it relates to electrical resistivity. We're going to introduce semiconductors and describe the role of dopants in modifying their conductivity. We'll talk about carrier concentration and how you measure it with Hall measurements. And finally, if we have time at the end, we're going to describe a few of the basic fundamentals of these basic semiconductor devices. And to start that off, I got a quick demo. This here is what's called, you've probably heard of it called as a Peltier cooler before. It's a thermoelectric device. And the name kind of gives it away what it does. Thermoelectric. What's it sound like it does? It's going to have something to do with thermo, so heat, and electric, so electricity, right? So this is actually a device that can convert to and from those two things. So for the first demo, I'm going to have Joseph hold this between his hands, count the sandwich, so you hold the heat on both sides. And he's going to tell us what he feels when I hook this up to a battery, so a 9-volt battery. First off, there's no moving parts inside of this. It's two ceramic plates and a bunch of little tiny metal legs that are connected together in series electrically and in parallel thermally. So what I'm going to do is I'm going to hook this up. I'll do positive and positive, negative and negative first. And what do you feel? Which side? The finger side? So this side is cold, the other side should be warm. If I switch the polarization, what do you feel? The opposite. So this is able to pump heat from one side to the other in real time, no moving parts, instantaneously. All right? It's very fast. It's not very efficient, but it's certainly great because you can cycle it on and off as quickly as you want it, and it can pump heat from one side to the other. So what it really creates is when I apply an electric field via the battery potential, right? What it creates is a temperature gradient, a difference in temperature from the two sides by pumping heat from one side to the other. But we could do this the other way around. I could set this on the table. The table is colder than my hand, and if I put my hand on one side, now I've established a temperature gradient across this device. And I forgot to bring it, but if we took a multimeter and measured it, we would measure a voltage between those two wires. So what I've made is I've made a battery out of my body, right? Out of my hand, the heat in my hand and the cold in the table. So these are thermoelectrics. Just take a second. I want you to talk to your neighbor and say, where on earth would you use this? Either for pumping heat from one side to the other by applying a current, or by taking advantage of waste heat to create electricity. Where would you use this and how? I want to hear some ideas. So talk to a neighbor for a second. Okay, let's hear what people think. So no wrong answers here, but where conceivably might you use this? Remind me your name. Sorry, one more time? Landon. What do you think, Landon? To cool computers. They use these all the time. If you are somebody who likes to operate your computer at a faster speed than is safe because it would generate too much heat, you can do something called overclocking where you manually set it to run at a higher CPU rate, but you have to do something with that heat. So they will absolutely take these things and they'll mount it right up next to the chip and they'll pull heat away from the chip to somewhere else. Copper fans, whatever heat sink you want to use, right? That's something you could use. What else? Yeah, what do you think, Kyle?
Is this what they use for like the brakes? For like the electric?
For regenerative braking?
Yeah.
No, I don't think so. I'm pretty sure not, but you could use it there. I don't think that's what's currently used, but you could. Regenerative braking basically, yeah, as you're braking on that, you could take the heat that's generated, or you could make it, the motion actually turn a solenoid. I think either of those would create electricity. I'm guessing it's the latter. I could be wrong. Where else could you use it? John?
I don't know if they do, but if car batteries get really hot these days, you can stick them on those.
Yeah, and pump it out to some sort, similar thing to like the processor, right? Pump the heat to somewhere where it could be dissipated. Yeah, what do you think, Conrad?
They use them in space exploration, don't they?
Yeah, so the Mars rover Curiosity, it's powered by these. You'd assume that it's powered by solar cells, right? It's actually powered by these things. The rover on Mars right now. How does it get its heat? Radioisotope. Yeah, it's an RTIG, right? A radioisotope thermoelectric generator. So it's actually taking polonium or whatever it is that's decaying. That's hot because it's constantly bombarding the casing that's surrounding it with particles. I don't remember what type, right? But it's giving those off. That creates heat. You slap these things all over it, and that's going to create energy in real time. So if you read The Martian, he wasn't making that up. When he goes and digs up the RTIG to get power, that actually exists, right, on the Curiosity right now on Mars. Okay, other questions or other places you can use it? Eating some delicious baklava. How is it? Is it?
Really, yeah.
It's amazing.
Yeah. Well, rather than using it, as a electricity to thermal properties,
Okay.
when I was been saying, we're thinking about power generation.
Okay. Where would you use power generation? How would you do it?
Think about what we thought about is like if you have your heater running on a cold day.
Okay.
By that very nature, your house to be warm and outside to be cold. So you have a heat temperature gradient putting these in your walls. That would work even better on like a spaceship, though.
Yep. One of the things you'll run into is that the amount of generate these generate is really low. Their efficiency is poor. It's like 5 to 10%. It depends on the temperature difference. It depends on stuff, basically. It's not high though. So if you're using energy to create heat in your home and then you're trying to scavenge this off of that, you're not going to do great. If you're going to have the temperature gradient anyways, sure, you could maybe scavenge something off. Where else might you use it? We'll do one more in the back. Is it Zev?
Manufacturing, because you're going to have certain heating and cooling processes where you
Absolutely.
bring up like a giant oven to do curing, and the heat's going to come out
Yep.
there, and you're going to use that.
A couple of years ago, I reviewed a proposal was on that exact same thing. They wanted to develop these things for the glass industry because when you melt glass, you got these giant crucibles, right? Anyways, and so you can run turbines off of that waste heat. But if you do these on top of the turbines to take care of the low-grade waste heat, you can get an overall more efficient process. So you could go on. We could list things all day long where you use these. This is one of the main things that we research in my group is trying to make better versions of these with lower cost materials, right? Higher efficiency, lower cost materials. For example, these use tellurium. Tellurium is the 9th rarest thing on the planet. You've heard me rag about this. Like, we should not be using it in devices. So we're trying to replace that with stuff that's much more common and therefore low cost. By the end of class today, if we have time, we're going to talk about why is it that an understanding of semiconductors and bands and band diagrams, right, and these energy gaps helps us understand how on earth these things actually work with no moving parts. So if we have time, we'll get to that next time. Otherwise, we'll do it Friday. So let's dive in today. We left off last time and we said, okay, that a band gap exists and the band gap changes with your interatomic separation. So if you bring things closer together or if you stretch them further apart, you can modify how big this gap is, right? It could be really big or it could be smaller. This is something that a guy in our department won a pretty big prize for recently. He worked on LEDs. LEDs require the existence of a band gap, and he basically grew a bunch of crystals by making them closer or further apart together. He did things to squeeze them or make them further apart, and by doing so, he could tune the band gap and make lots of different colored LEDs, which has led to, LEDs are everywhere now. And solid-state lighting is making a very big difference in terms of energy consumption in residential commercial spaces. So that's the first thing to realize, that this band gap can change with respect to interatomic separation, but your materials typically have a band gap, but where you're operating at, meaning where you fill your electrons up to, maybe you only have electrons that fill up to this level. So for that material, at its highest occupied energy level, it's still right in the middle of a band, okay? But you might have a material where its highest occupied energy level is right in the middle of the band gap. Whether that happens or not dictates whether you have a metal versus a semiconductor versus an insulator, right? So let's show what I mean by that. So again, if you have an insulator in these diagrams that I've got here, red means that it's filled with electrons, right? So you have X number of electrons in your compound. They fill up in terms of energy. This is increasing energy on the y-axis. They fill up right to here, and you're what's called the Fermi level, the level at which they stop filling up at 0 Kelvin. I mean, if you froze this down to as cold as it could go, is somewhere in the middle. So all of these are empty seats. They're spots where electrons could occupy if only they had a way of getting across that band gap, jumping up there, right? So really the way to think of this, I think the best way to think of this visually is like a double-decker bus. So if you've seen the pictures of the double-decker buses, imagine that you're on a double-decker bus in England, right? And you're sitting on the bottom floor, and if you're the only person on that bus, then you're sitting in a partially occupied band. It would look something like this, right? You've got some number of electrons, but you've got lots of empty seats. You've got a band gap, and then you've got the conduction band. If there's only one person on the bus and you want to move from the front of the bus to the back, you could hop from seat to seat to seat because they're open, right? That changes if you fill that bus up with people. Once you've filled the bus lower level up with people and all the seats are filled, then it becomes difficult for you to move around on the bus, right? Because you can't hop from seat to seat, right? So your conductivity, your electrical conductivity, your ability to conduct electrons actually goes down if this is your situation. Unless you're willing to expend the energy to climb up the stairs to go up there. If you climb up the stairs and go up there, now you've got an electron in what we call the conduction band. And you have the lack of an electron, that little hole there, in the valence band. So if you do that, if you're willing to spend the energy to climb up the stairs, now you are free to move as the electron in this top deck of the double-story bus, right? Plus, you created a seat below you. So now people below you, they can move around because there's this empty seat that people can hop to, right? So you basically benefit in two ways. You create what's called a free electron, or an electron that's mobile. It can move around in an empty or a partially filled band. And you also created a hole. A hole is just a spot where an electron used to be. Okay? Any questions so far on this? Yeah, Rosa?
Why is it illegal for the electron to hang out in the band?
Good question. We're not going to go into detail in this class, except to say that there is no valid energy level. Has to do with the formation of these bands. An introductory course in solid-state physics, we'll get into that. We're not going to cover it in this class. So for now, you're just going to take my word for it that there exist regions of energy where you cannot occupy. Okay? And that for different materials, those regions will change a little bit. They're tunable. Okay? Any questions on the whole jumping up from the valence band to the conduction band? So if you've got a semiconductor versus an insulator, this distance between the valence band and the conduction band, the band gap as we call it, is going to be small. If it's a small band gap, something like 1 or 2 electron volts, then thermal energy, if you heat this thing up, gives it enough energy for these electrons to start to jump up. So see how it's pink in the conduction band and kind of pink below? If it's solid red, that means it's 100% occupied. The pink means it's kind of occupied. There's some electrons that are able to get up there. So you'd expect a semiconductor to kind of conduct electricity because some of your electrons have jumped up, creating holes below, right? If you have a metal, like a conductor, then your bands overlap, right? These are two bands that don't have a band gap. They just overlap. So there's empty seats. Imagine this like a bus that's like really, really long. It's just got empty seats, right? You just keep on filling people in there, okay? Any questions? Yeah?
So like, does the fact that it can like a semiconductor or an insulator or conductor have to do with just the size of the band gap or the how full the band is?
Great question. Has to do with how full the, well, it has to do with what we call the Fermi level, right? The Fermi energy, again, that's at 0 Kelvin. If you were to cool this all the way down, that means that there is one energy level that you would fill up to. Like, let's say that this would fill up right to there if it was at 0 Kelvin. Now that metal right there, this conductor, is not at 0 Kelvin. And so because it's above 0 Kelvin, some of your electrons are going to have higher energy. They can occupy slightly higher. And you'll have some missing spots just below that Fermi level. So your question is, what's the difference between semiconductor and insulator? Is it the band gap? Is it the Fermi level? It's both, right? Because take this thing. Imagine this scenario. Let's say you've got a really big band gap, and then you've got a band down here, but this is where your Fermi level is, right? If that's where your Fermi level, even though there's a pretty big band gap here and there's a big band gap there, it doesn't matter because this thing can conduct because there's empty seats right there. So this would be a metal. It's a metal that has a big band gap, but that when we talk about band gap, we're typically referring to you filled the valence band, you have an empty conduction band. That's what we call a band gap. So technically are these? Yeah, sure, but we wouldn't say that this metal has a band gap because its half-filled band means it's going to keep conducting. Yeah?
So if you had something like that, would there be a limit to how much current you could try to push through something like that? If you're trying to do like half a valence band, for example, but then if you try to go above that, you go into the band gap? Is there like
Yes, yeah, let's come back to that in a minute when we get to semiconductors, like silicons. We're gonna come back to that exact question. Other things I can answer so far. This is typically a point of confusion for students. Is this topic? Yeah. Other question?
Might be a little off topic. Maybe that is that where they got the idea for superconductors, that they cool it down?
No, but good guess. Something different happens with superconductors. There, you get high conduction because electrons stop behaving like we expect them to. Normally, if you have two electrons, they repel one another. In superconductors, below a critical superconducting temperature, these things pair up. They form a Bose-Einstein condensate, right? They condense into like this new particle. That new particle doesn't give a rat's about the lattice. It just flies right through it. We don't understand this. This is a Nobel Prize waiting to happen when somebody figures out what on earth is going on there, right? We have some ideas, but we don't understand it. Okay, so that's metals versus semiconductors versus insulators, okay? We talked about valence and conduction bands. Okay, let's talk about intrinsic semiconductors. An intrinsic semiconductor, that's one that we don't dope it to make it conduct electricity. Instead, what we do is we heat it up, right? So this guy right here, the Fermi level's in the middle of the band gap, right? And we're talking about this one. But if you heat it up a little bit, you provide energy for things to hop up a little bit. And the hotter you get it, the more energy you give it, the more those are going to hop up to the conduction band. So you would expect in this material that the hotter it goes, the higher the conductivity, because you have more carriers, right? That's the opposite of metals, by the way. Metals, when you heat them up, the lattice starts to vibrate more and more. So this is a metal over here. That one, you don't need to heat it up to get carriers into empty seats. They've already got plenty of empty seats, right? This thing's half filled. So you've got all sorts of empty seats for conduction. But when you start to heat it up, now the atoms are moving around a lot, and it scatters the electrons. We'll show you what I mean by that in a moment. So you get completely different temperature dependence. In one, if you were to plot, say, the conductivity versus temperature, and if you observe that it increases higher conductivity with temperature, then you would say that this is a semiconductor. And on the other hand, if you see something that goes down with temperature, then that would be a metal. Metals are typically have higher conductivity than semiconductors, so I drew my axis funny. Yeah, Matt?
So for an insulator, is there a point where you heat it up enough that it will conduct?
Absolutely. Yeah, things that do not conduct at room temperature, like zirconia, a ceramic that does not conduct electricity, heat it up to, I think it's around 13 or 1400 Celsius, and it's like a metal, right? It's very conductive. You can actually make furnaces out of it, where that's where the induction coils come from, is zirconia, basically. So you heat it up with graphite coils to get started, and once it's hot enough, then that actually becomes your heating element. So that happens, absolutely.
Is there anything that, like, no matter how hot it goes, it just never conduct? Or
You'd have, well, the bigger and bigger the band gap, the higher and the higher the temperature that you'd have to go to. And you might reach a point where your material decomposes, either melting or whatever, before it reaches that point of having significant conductivity. Okay? So things that have huge band, like alumina has like a huge band gap. Okay? Okay, so that's basically how understanding what we call band diagrams and band gaps and the Fermi level helps us differentiate between metals, insulators, semiconductors. And again, intrinsic semiconductors are ones where we just rely on temperature to jump across that gap. There's also something called extrinsic, right? Before we talk about that, let's talk about the Fermi level, right? So this is the probability of occupancy on the y-axis plotted against the energy, right? So at 0 Kelvin, if you cooled this thing completely down, all the electrons are going to stop moving, right? We can't reach 0 Kelvin, but if you could, basically you would fill it 100% up to some energy level, and then you'd have 0% occupancy for everything above it, right? So the Fermi-Dirac distribution basically says, okay, in the real world, you're going to be above 0 Kelvin, so you're going to have a little bit of energy for your carriers. So what you see is that the higher and the higher the temperature you go, say going from black to red now has some empty spots, and then over here you've got some filled spots, right? And that distribution gets what we call softer and softer the higher temperature you go. So higher and higher temperatures, it starts to be more sigmoidal like this. We call that a soft Fermi-Dirac distribution. And if it's a really sharp one, we call that a sharp distribution, right? Or a hard Fermi-Dirac distribution. Any questions so far? This is tricky because we moved our energy axis on the horizontal. It's usually plotted vertically, but in this graph they did it horizontal. Yeah, Rosa?
Would it explain again why there's that?
Well, because let's say you've got 100 electrons, right? And at 0 Kelvin, all 100 of those, you've taken away all their kinetic energy. So they're just going to collapse to the lowest energy level they can find. Okay? That makes sense? So that explains why you have 100% occupancy, 0% occupancy. Now let's say you give it a little bit of thermal energy. Out of those 100 electrons, 1 or 2 of them might be your outliers, and they might have a little more energy than others. So they're going to jump up and be able to occupy these empty seats. As long as there are empty seats, they're going to be able to go up, and they'll create holes where they were before. So that's why you see this sort of shape where you get less occupancy at lower energies and a little bit higher occupancy above the Fermi level. Okay? Maybe it's easier to think of it in terms of the band, right? So again, yeah, Arthur?
So that would be insulator in the example you just showed, what it looks like.
It depends. If this is the end of your valence band right there, and you occupy all these, and then there's a band gap, and then the conduction band, that'd be an insulator. If instead you had a band gap like this, and you only filled up to some arbitrary point, but these are empty seats, that would be a metal. Okay? Let's talk about it in terms of conduction band, right? So on the far left, here you've got a semiconductor or an insulator. Your Fermi level is shown right here, right? So basically you completely fill your valence band, okay? But you don't have any in your conduction band. Now if you go above 0 Kelvin and start to give it thermal energy, some really small fraction of your electrons will occupy that, and some fraction of them will have been removed from your valence band. So you created holes and you created electrons in the conduction band. So this would start to conduct. If you heat it up more, now you're getting even more up here and more down here, so it would conduct even more. So this explains why, again, a semiconductor, plotting electrical conductivity versus temperature, more carriers means more electrical conductivity. It goes up with temperature. Yeah, Matt?
Just to be semantic, but why is the size of that difference in the conduction band versus that high temperature valence band?
I've not seen it like that before. Typically, they draw it symmetric. Yeah, I don't know why they chose to draw it that way. That's a good question. Okay. Any questions so far? Yeah, Jeff.
So the only electrons that go to the conduction band are the ones that are above the energy gap.
This cutoff, which they're calling it E gap, yeah. But that cutoff of energy, whatever we want to call that.
Even though they have a higher energy, they're still down in the valence band.
Yep. Because they don't have enough to get up there, right? It'd be like if you could climb the double-decker bus, you could conduct, but you're only able to climb 9 of the 10 stairs. Not good enough. You got to get up all 10 of the 10 stairs.
Then you fall down. You can't sit in the gap, right?
Can't sit in the gap. These are unoccupiable states. Okay. So clearly thermal energy is one way to get conduction. You can heat something up and bump electrons up. What else could you do? Maybe chat with a neighbor. What else might you do to get carriers from the valence band to the conduction band? There's one main one. Anybody got an idea? Something stand out? Yeah, Jeff, what would you do? Use radiation? That's absolutely what you'd do. So let's say you've got a gap, right? You've got this thing totally filled, but let's say you bombard this thing with a photon, say from the sun. It hits an electron, absorbs the energy, that electron hops up, creating an electron here and a hole down there. This is the principle of how solar cells work, right? Solar panels, which we'll get to later this class or maybe on Friday, they are basically just semiconductors where you tune the band gap to have the same energy or similar to energy as the light coming in from the sun. That light comes in, promotes it up, and then what you need to do is you need to separate it. You need the electron to go that way and the hole to go that way so that you create, a current out of this thing so you can charge your home or your car or whatever. And so how you do that, we haven't gotten to yet, but there's a trick that they do. For right now, just realize it's possible. Okay. We talked about that already. Okay, let's talk about mobility for a minute. So we have our next clicker question. Our next clicker question says the following. Oh, pause that. Just close it. Okay, it's true or false. If an electric field is uniform, what's an electric field again? That's a voltage difference divided by some separation, right? So that's our electric field. So if that's uniform, it's unchanging, then a charge carrier, an electron or a hole or an ion, any of those three things, they will continue to accelerate continuously within the field. So let's say your field goes from here to here. If I put a carrier in here, Since it's in a field, it's just going to keep on accelerating as long as it's in that field. Once it's out, it stops accelerating. That's the question. True or false? Yeah, Brennan? Let's say it's in a substance right now. Yeah, good question. In a substance, like in a piece of metal. You've hooked a battery, you've hooked 2 leads of a battery up on either end of the metal. Will the carriers accelerate constantly or will they not? Okay, answers in. True or false? Okay, we're going to end this one. Oh, sorry. Wow! Okay. Takara, will you send me an email after class? Tell me to add a point for either one on that, or I'll forget. Okay. So we'll give you credit either way on this one. That's a perfect split. So I want to hear what you think. Who thinks that it will not? Who voted false? And who voted true? And I want to hear your rationales. Who voted false? Josh, what do you think? What's your rationale?
I think the electrons will hit stuff while they're traveling through the substance and stop accelerating.
That's a good guess. Basically, okay, who thinks the other way? Anybody think the other way? What do you think, Landon?
I think true because, you have a wire hooked up to a battery, there's going to be a charge running through that wire constantly.
Yeah, well, what do we know about charged particles in electric fields? They do experience an acceleration, right? It's got this Lorentz force on it. A Lorentz force is going to be a force that's, right, it's not a net force, or sorry, it is a net force. It doesn't have something acting against it. So it will accelerate. But then Josh's comment is actually correct. These will, let's see, how was it phrased? Will it continuously accelerate? It will not continuously accelerate because it's going to experience a drag, basically. It's got this force from the electric field that says keep on hurrying up, but as it's moving through the lattice, it's going to bounce into things, and that's going to be like a drag force. So it's the same reason that if I jump out of an airplane from really, really high up, I will accelerate because I'm in a gravitational field, right? It's no longer charged particles electric field, it's mass in a gravitational field. So I will accelerate towards the ground, but I won't just keep on accelerating. We hit what we know is called terminal velocity, right? Because at some point, the acceleration from gravity, which exists, puts a force on me, is going to be countered. The gravitational force is going to be countered by the drag force from the air, right? So you reach a terminal velocity. So the exact same thing happens in electronics, right? They reach a terminal velocity by drag. Now, how do we quantify that drag? We call it mobility, right? So an electric field causes electrons to accelerate in the direction of the field. It causes holes to accelerate in the direction, opposite versus same. The holes go in the direction of the field, electrons go opposite the field, right? But there's something that's going to make it drag. So you can think of it as a frictional force. That's one way to think of this. Here's a diagram of what it might look like. Imagine you've got an electron that's traveling from one side to the other in these different things. If you don't have very much friction, or if you don't have very many scattering events, your electron will travel mostly uninhibited, and it might occasionally hit something like this guy right here and have a small scattering event and then get right back on its way again. But you could imagine a different material where it scatters a lot and it goes backwards a little bit and it goes forward, and overall it travels that way, but there's a lot of scattering events in between, and you can imagine all sorts of things, right? In the case on the far left, what's called the mean free path, the distance between scattering events is quite large, but there's not that many scattering things. In figure B, the mean free path is really small, right? And there's lots of them. So there's lots of ways that you could tune this. Now, what's going to cause things to scatter? Clearly atoms. What else might cause things to scatter? If you're an electron flying through, we've got a whole list here, actually. Other electrons, imperfections in the lattice, like a vacancy, impurity atoms, dislocations, grain boundaries, thermal vibrations, all these things can mess up your ability to move through a material. So again, going back to electrical conductivity versus temperature, if you're a metal, you go down because thermal vibrations really start to take off. You've got lots and lots of carriers because you're a metal. Your Fermi level is right in the middle of a band, so you've got plenty of carriers. But as you heat it up, atoms vibrate more and more. So if I took like a wiffle ball and I tried to roll it up the floor of this room, and you guys held your feet perfectly still, the distance that wiffle ball could go would be, some distance, 20 feet or something. But if at the same time I take the exact same wiffle ball and I roll it at the same velocity, but now you're moving your feet around like crazy, it's not going to go that full 20 feet. It might go 5 or 10, right? That's exactly what's happening with thermal energy in a metal. So that's why your metal conductivity goes down. So in an insulator or a semiconductor, you still have thermal vibrations messing things up, but you compensate it by creating tons more carriers that can jump across the gap. So overall, it's net positive for semiconductors, insulators. Okay, so the drift velocity is your terminal velocity. So V sub d, we can write the expression for V sub d, that's equal to mu sub e, that's the mobility of an electron, times the electric field. So if you could figure out on average how fast your electron travels through this thing, that's V sub d, that's the velocity it travels. If you know what the electric field was, you could then take V sub d, divide it by the electric field, and that would be your mobility. So the mobility for either electrons or holes is just going to be a measure of the friction forces that it moves as it feels moving through it. So higher mobility, higher electrical conductivity. Lower mobility, lower electrical conductivity. So how does it relate? It looks like this. Conductivity, sigma, that's electrical conductivity. That's going to be equal to n, the number of carriers we've got, times the charge of each of those carriers, absolute value of E, your fundamental charge, multiplied by the mobility, right? What would this be for holes, right? If it's not electrons moving through the lattice, but holes, we can rewrite this. We would say for holes that our conductivity is now going to be, we write it as P. P is the number of holes in a lattice. And remember, hole is just a missing electron spot. And to make that connection, right? There's an empty seat next here to Joe. So Joe's the electron. This is an empty seat. So this is the hole. But by the virtue of this hole existing here, Joe could get up and move there, right? So you can create, the hole would move that way, Joe would move this way. So you can have electrical current just by having these things there. So if you haven't thought of holes before, just think of it as a spot where an electron could be. So the conductivity due to holes is going to be P, which is the number of holes per some volume, right? Times the charge of a hole, which is just the charge of an electron, and then multiplied by the mobility of the hole, mu sub h. Okay? Any questions on this so far, on how you go from mobility to electrical conductivity? So if I gave you the number of carriers, n, if I gave you the charge, 1.602 e to the negative 19 coulombs, and I said what the mobility was, you could all calculate the electrical conductivity. Okay? Yeah, Rosa?
So, if n is electrons and p is holes and e is just e, what is mu, e, and h?
Mu e is the mobility of the electron. Mu h is the mobility of the hole. And naively, you would expect those to be the same. And when you take a course in solid-state physics, you'll learn that they're not the same, that they're different, that they don't have the same mobility. A hole and an electron experience different friction forces as they move through the lattice, even though a hole is just a missing electron. They experience different mobilities. Okay? Any questions so far? In the back? Is it Barzan? Or Mohammed?
Yeah. So in general, would it be less of mobility on the hole or more mobility than an electron?
In general, and this is very general because there are exceptions to this, electrons are more mobile than holes. But it totally depends on your material. The book has some great tables that show you what it looks like. And it depends on what material they're in. So an electron in silicon does not have the same mobility as an electron in, say, germanium, right? They're going to have different mobilities, okay? So it's material dependent. And it's temperature dependent, right? That makes sense because temperature, that's basically accounting for thermal vibrations. So mobility is not constant. It goes down with temperature, okay? P is the number of holes per unit volume. So it could be like 10 to the 20 holes per centimeter cubed. Yeah, Arthur?
So I have a question. Shouldn't the conduction be because of holes and also because of the number we have?
Yeah, we're going to come back to that, I think, very soon. Intrinsic conductivity, we would write it as this. We would write N E mu sub E plus P E mu sub H, right? If we go back to our diagram, you're absolutely right, Arthur. If you go back up here, basically we said in this picture, by heating it up, you created holes here by these electrons jumping, chipping, going up there. So both of these should contribute to electrical conductivity. You're absolutely right. In an intrinsic semiconductor, you have to include both terms. You can't just say one or the other. Now, why do we ignore one or the other? Because oftentimes we dope it so that either the electrons or the holes is way bigger than the other, right? Maybe there's like 1 billion times more electrons than there are holes, which means the fraction of conduction coming from holes is negligible. That's usually why you consider one or the other. But in an intrinsic material, you cannot. You have to take into account both. Any questions? You're right, Rob.
Sorry, just checking. So P is number of holes per unit volume. Does that mean that N is number of electrons per unit volume?
Correct. Yeah, P and N correspond to the number of holes or electrons respectively per unit volume. Okay, something else to talk about is Matthiessen's rule. Matthiessen's rule just says, okay, if you have something that's causing resistance in your material, something that's slowing down your electrons, these things can be added up, right? So here's an example. Start with pure copper at some temperature. Maybe this is around room temperature. That's your resistivity. Now you dope it with 1.12% nickel. So you've got impurity atoms. That raises the resistivity because now instead of having pure copper, you've got other stuff that's going to cause them to scatter. And then you say, go a little bit higher, right? You add more nickel. It's going to increase the resistivity further and so on, right? But you could also say, okay, what if you add, they deform it. There it is. By deforming it, you create dislocations. Dislocations slow it down, right? So these things add up. So it's basically saying your total resistivity can be thought of as contributions to your resistivity from a bunch of smaller things. Thermal, impurities, grain boundaries, surfaces, whatever it is, okay? And as I've said, in a metal, your resistivity rises with temperature, or your conductivity falls if that was conductivity. Your metals become worse metals the more you heat them up. Your semiconductors and insulators become better at conducting electrons if you heat them up. Okay? Just a few things to note. Right now, if you want the very best electrical conductor, there's something called oxygen-free high conductivity copper, or OFHC copper. That's basically as good as you can get in terms of conducting. Almost. You've got aluminum, which is about half the conductivity as copper, but it's about a third of the price, right? So price, if you're looking at the best conductivity per price, aluminum's the way to go, which is why they used to use it in homes, right? It was better. Silver is actually a little bit higher. If you make any solid solution, so a mixture of atoms, your conductivity is going to go down. If you deform it, your conductivity goes down. Those are some general things there. Okay, let's talk about semiconductors now. We've already said what intrinsic semiconductors are. More often than not, we don't use intrinsic semiconductors. Instead, we dope them, right? We dope them to have something that changes the conductivity. Here's how it works. Okay, start with let's see. I'm going to skip that for now. All right, let's consider a lattice of silicon atoms, right? So I'm going to draw silicon here, silicon here, silicon, silicon, silicon. Okay, in the case of intrinsic electrical conductivity versus extrinsic, we're going to dope it, right? So if these are all silicon, silicon has 4 electrons, right? And so in order to have 4 bonds, which it wants to have, it's going to share these electrons with 4 others, right? So for each one of these silicons, we could draw electron, 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 electron. This guy's got electron, 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 electron. So that right there, that's a bond, right? They're sharing that right there to create a bond. This guy's got electron, 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 electron. So all of these are bonds, right? And we know that atoms want to have these 8 bonds, right, in this p orbital. So all of these electrons are tied up in these bonds and they cannot leave, okay? They're basically busy, right? So what we do with extrinsic doping is we take out one of the silicons and we put something else in, right? So imagine that we put in, well, first off, if you did want to make this thing conduct, you'd have to give it enough energy to break this bond, right, for this guy to leave and become an electron. Oh, it's gone. Not today. Okay. So you break this bond, you move it there. Now you've got a free electron and you have a hole, right? Which is positively charged. So your electron is negatively charged, your hole is going to be positively charged. Now that you've done that, if you apply an electric field across this thing, if that's the direction of your electric field, we know that the hole will travel that way and the electron will travel that way, right? So that's intrinsic semiconduction, okay? So, as Arthur correctly, I think, noted, your total conductivity in the intrinsic case, you basically have to account for both of those, the electron and the hole being able to move. Now let's talk about extrinsic. In extrinsic, you've doped it with something. So let's go back to our lattice. We've done silicon, silicon, silicon. Which one do I do in my notes? Let's do boron down here. Silicon and silicon. So all of these have 4 electrons, except for boron only has 3. Right? So let's say it's got a missing electron. Right? So all these things are happy and satisfied, except, right, these are all bonds. But this right here is not a bond, right? Because it's missing an electron. We doped it intentionally to have a missing electron. So what does that do? How does that lead to higher conduction? Anybody? Yeah, that's a hole, right? It's a missing electron. That by definition is a hole. Therefore, for conduction to happen here, let me change a different color. This electron could hop there and fill that hole and move the hole over, right? So all of a sudden this thing is conducting. All we had to do was we picked something, if our base semiconductor had 4 electrons for all of them, we put in something that only has 3. That created a hole. What else could we do to make this thing conduct? Put in something that has more. So instead of this silicon with 4 over here, let's put phosphorus, which has 5. So it's got its 4 that it normally has, right? But now it's got some extra one. It's got a 5th electron, right? This guy's just hanging out. So now when you apply a field to this thing, the phosphorus is bonded to that extra electron, but it's not bonded very tightly. It's what we call a loosely bound donor atom, right? So this is a donor impurity because it donates an electron. So it does take some amount of energy to strip this thing away, right? For this electron to move, it does take a little bit of energy to pull it off the phosphorus, but not very much. It's what we call easily ionized. We can ionize that phosphorus to become +1, right? When the electron leaves, phosphorus becomes +1 because we lose the one from the electron leaving. Meanwhile, boron becomes 1 negative when an electron hops there, right? So both of these are easily ionized, way more easily ionized than taking a silicon and making it jump across the gap. So I think the easier way to think of this is in terms of a band diagram. So let's go back to our silicon. Silicon looks like that. The silicon with phosphorus, p-doped, looks like that. And the silicon with boron doped is like this. So what do we need to do to these? This one, for electrons to get across the gap, you got to jump the whole thing. In phosphorus, you've still got a filled gap here, right? If we go up to this thing, in the phosphorus case, all the bonds are still satisfied, so there's still the electron gap, but you've got this one extra electron. So how we draw that is we say that it has a tiny, for every phosphorus, you've got an electron right there, and it only has to jump a really small gap in energy to get to the conduction band. Meaning it only takes a little bit of thermal energy for that thing to become ionized and leave behind a positively charged donor ion. Over here, boron, this thing is still filled, but now we've got an empty state right there and only a little bit of energy to take an electron, fill that state, and create a hole. This makes sense? Any questions on this so far? Yeah, Arthur?
Can we just, before the last, can we just write the thing as not fully filled instead of having, like...
No, because it's fundamentally different than that. This is an energy that you have to overcome. If we just wrote it as not fully filled, you'd say, great, it should conduct like a metal. But that's not what these are. These do take a little bit of thermal energy. It takes a little bit of energy to jump up and fill that. Or in this case, it takes a little bit of energy for this extra phosphorus atom to jump up and fill the conduction band, right? So it's not the same as just drawing it that way. And what it leads to is a pretty important difference. So if we look at our conduction band as a function of temperature, it leads to this behavior. This was the clicker question, right? The clicker question said you've got these 3 regions. If you take a semiconductor that's been doped, so an extrinsic semiconductor, it's got phosphorus or boron or whatever, you're going to have at low temperatures, so this is electron density, it's going to plummet towards 0. So if you cool this thing down to absolute 0, you take away that little bit of energy that it needed to ionize the phosphorus electron or the hole to come over to the boron. So basically it takes a little bit of energy, not very much, and you take off. And you're going to reach some plateau value. That plateau value will be dictated based off of how many dopants you added to this. Did you only add a few or did you add a bunch? If you didn't add very many, your concentration won't be high. But if you really doped it heavily, you're going to have a higher conductivity. But let's say you keep on heating this thing up. Basically, nothing is happening here because, again, going back to our picture, in that middle region, you have enough thermal energy to jump from here to here. But for a big stretch of temperatures, you have enough to jump from here, but you don't have enough to jump all the way up there. So nothing happens. Your carrier concentration isn't changing for a while until you get to a high enough temperature that you can start to jump across there, and then you're going to see your carrier concentration take off again, and that's what you see in these diagrams. Right? If you heat it up enough, there's the This is called the freeze-out region over here, where it's such a low temperature you can't even ionize your dopants. You've got the extrinsic region in the middle, and then over here you've got your intrinsic region on the right, where after a certain point, the number of intrinsically generated carriers starts to dominate and become larger than the number of doped carriers that you added. We will pick up here next time.